everyone, and welcome to this video on solving absolute value inequalities involving the is greater than symbol or the is greater than or equal to symbol. In this video I have several examples of inequalities of this nature where we're going to eventually get down to having the absolute value of a single linear expression on the left side, and then is greater than or the is greater than or equal to symbol, and then some number, some real number on the other side, and going through the process of solving, figuring out what numbers I can replace the variable with to make a true statement. So let me begin. My first example has my instructions, what am I be asking myself to do here. So I'm going to be solving each inequality, finding all the numbers that I can replace the variable with to make a true statement. And then I'm going to express the solution set in set builder notation, interval notation, and also make a graph of the solution set on the real number line, right? And because there's only going to be one variable in each of these, we're just drawing a picture of the solutions, a graph on a single real number line. Okay. So in each of these, we're going to be taking a look at inequalities of this form, or we're going to want to put all of the inequalities we see in the following form, where I have the absolute value of some expression, which I'll call A, on one side, and then is greater or is greater than or equal to. So I'll put this in another color because sometimes the or equal to symbol will be there. And then on the other side, a real number n, right? I'll just put n for number. Okay. So I want to eventually get down to a form like this, so that'll be the first step in solving these. And so I'll come down here with the steps I'm going to follow to solve these inequalities. First, I'm going to isolate the absolute value. Okay, so get the expression like this absolute value of A, or over here in my example I have the absolute value of X, is greater than or equal to 6. I want the absolute valued expression on its own, isolated on its own side. Nothing multiplied by it, it's not divided by anything, nothing added to it or subtracted from it, just the absolute value on its own. Once that's done, and if you've seen my video on solving absolute value inequalities with the is less than or equal to symbol, or even the a video I put up on solving absolute value equations, after isolating the absolute value, we're going to use the what does absolute value mean? We're going to use the concept of absolute value, how absolute value can represent the distance from 0 on the real number line when we're talking about the absolute value of real numbers. We're going to use that concept to rewrite our inequality as an equivalent compound inequality. So again, let's think about that. I'm going to have inequalities of this form, where the absolute value of some expression A is greater than or is greater than or equal to, and then some number, some real number n. Now my hope is that this is a non-negative number, so we can actually talk about distance from 0 on the number line. What does it mean to have an absolute value greater than n. Well, let me describe what that means down here. So when I say the absolute value of, this number a is greater than n, what does that mean? That means that a is more than n units away from 0 on the number line. So whatever this expression inside here is, whatever this number is a, it means that a is more than n units away from 0. On the real number line. And in fact, I'll draw a little picture representation next to this. So suppose this is the real number line here. Here's the number 0, and you just need to think of what numbers have an absolute value equal to n. The number n. Again, I'm hoping that n is a non-negative number, so it's to the right of 0. That's n units away from 0, and so is the opposite of n, right? Like negative n or negative 1 times n. That would also be n units away from 0. So the numbers we're talking about here, the numbers that have an absolute value greater than n would be all the numbers that are farther than 0, than n units from 0. So all these numbers, to the right of n, right? These are farther, these are more than n units from 0. Same with these numbers over here. All these numbers to the left of the opposite of n are more than n units away from 0. And that sets up our inequality. Now, if I have greater than, I'll put an open point here, but I'm not worried about what happens at n and negative n yet. I just want to know that we're writing an equivalent statement. All right, we'll use a little double arrow here. So this statement saying that the absolute value of a is greater than n, or greater than or equal to n, is equivalent to saying that, and again, look at this picture, that a, right, this number inside the absolute value symbol, a, is left of negative n, so is either less than, right? So I know it's weird with the change in symbol, but either a is less than or equal to the opposite of n, or, right, big word here, or the number a inside here is one of these, to the right of n, or greater than n, or greater than or equal to n. And this is huge right here. This is what we're rewriting. Okay, we're rewriting our absolute value inequality like this, as this compound inequality involving the word or. Notice it's not connected, right? You do not connect these. There are no numbers that are both over here and over here at the same time. All right, so it's got to be the word or in between these two inequalities, making it a compound inequality. And it's not connected like it was when there was less than or equal to, and again in my previous video if you want to watch that. Alright, so I'm going to keep writing the word or. That will never go away for these greater than or equal to inequalities. Alright, so let's think about this example here. All right, here we see the absolute value of x is greater than or equal to 6. Alright, so I have the absolute value isolated, right? It's already done for me. It's already written that way, all alone on the left side. Then I'm going to write this as an equivalent compound, second part, right, as an equivalent compound inequality. This statement here is equivalent to, which again I'll use a double arrow in the future, but right now I'll write is equivalent to the following statement. And just think, what does it mean for a number to have an absolute value greater than 6? Or even equal to 6, but having an absolute value greater than 6 means that this number x is more than 6 units away from 0. So imagine the n here and negative n, that's 6 and negative 6, right? 6 is 6 units from 0, negative 6 is 6 units from 0, and the value of x that we need to plug in has to be more than that 6 units away from 0. Now you could just go through and have this also memorized if you want. You know, the x is like the a, and the 6 is like the n. So then we write our compound inequality, saying that the absolute value of x is greater than or equal to 6 is equivalent to saying that, x needs to be less than or equal to negative 6. All right, this is all the numbers left of negative 6, all the numbers farther than 6 units away from 0 on the left side of the number line, or x, right, the number inside the absolute value symbols, needs to be greater than or equal to positive 6, right? And this is all the numbers that are more than 6 units away, to the right of 6, the right side of the number line. All right, so then after doing that, after writing our absolute value inequality as an equivalent compound inequality without absolute values, right? Notice in this compound inequality here, there are no absolute value symbols. I'm removing those. Then the third step, solve the compound inequality. And of course, verify your solutions. Now it's going to be hard to check every possible solution, right? So I'm just going to say, pick a few, go through several examples just to make sure, just to see that you believe. It's not a proof, but just to see that you believe that the solutions you've written are right. Because chances are, if 4 or 5 numbers that you say are solutions actually work, you probably did okay. Right. All right. So now remember how to solve. I did put up a video prior to this on solving a compound inequality involving the word or. You solve both of them separately, and then you find the union of the solution sets of the two inequalities in the compound inequality. All right. Well, let's do that here. Now these two inequalities are already solved for, right? The variable x is already alone. So there is a perfect description right here. I'll maybe underline it. There's a perfect description then of all the solutions to this inequality. You can plug in for x, any number less than negative 6 or negative 6 itself equal to negative 6. Or you could also plug in any number greater than 6 or equal to 6, and this would be true. And then again, let's verify. Well, let's just pick some examples. How about negative 7? That's less than negative 6. How about negative 7? If I replace x with negative 7 in the original inequality, the absolute value of negative 7 is positive 7. And is 7 greater than or equal to 6? Yeah, 7 is greater than 6, so that's true. And go ahead, try negative 8, negative 6.5, negative a million, negative a billion. Anything less than negative 6 or negative 6 itself should make this true. Or, and then over here you have another group of solutions, numbers greater than or equal to 6. All right, well, 6 works. The absolute value of 6 is 6. 6 is indeed greater than or equal to 6. It's actually equal to 6. And then plug in 7, 8, 9, 10, a million, a billion, 6.1, 6.25, 7.5, 7 3/4, 8.5, whatever. Any number greater than or equal to 6 should make this original statement a true statement. All right. Now, we were asked to express the solutions in certain ways, right? We have a description of the solutions right here. After I've solved my compound inequality, there's a description of all the solutions of this inequality. But then we were asked to slide this back down. We were asked to express the solution set in one set builder notation, which I'll tell you right now that's a pretty simple one. If you've already solved your compound inequalities, here we go, I'll just do this down here. If I want to express that set of solutions in set builder notation, I write the curly braces, right? Just make a little s and a backwards s, little curly braces to start a set. And now the variable in this inequality is the variable x. So I have the set of all values of x, right? The set of all values of x such that, right, little bar here meaning such that, or as long as, or you sometimes might see a colon, just 2 dots. And then after the bar or the colon, there's a description of the values of x I can plug in, a description of the values of x that are actually in the solution set. So I can use any value of x I wish as long as it's a value that's less than or equal to -6 or greater than or equal to +6. All right. So all I did was write my solution to the compound inequality in this description area after the bar. All right. So this is called set builder notation. Then I like to make a graph, right? We were asked for a graph. Back up here, graph the solution set. I like to make a graph before I write an interval. You can do either order, it doesn't matter, but let's make a graph, right? So there's a single variable, right? So I have a single real number line here. Pop 0 somewhere to separate positives from negatives, and just I'm just drawing a picture showing where all the solutions are. All the numbers less than or equal to -6. So here's -6, right, to the left of 0. All the numbers less than -6. So all these numbers over here, forever, or equal to -6. So -6 is a solution, and if a number is a solution, it needs to be solid. Right, a nice solid dot, solid point, something solid above it to indicate that it is actually a solution. It is actually part of the set. Or you might also see somebody put a rectangular bracket here, but I like to put the solid point for a solution and an empty point or an open point or a hole for a non-solution. All right, so those are all the numbers. Those are some numbers that are solutions. Or, right, in union with, we do the union of this set with this set. All the numbers greater than or equal to 6, +6 over here. +6 is a solution, so again a nice solid point, and then all the numbers greater than 6 are all indicated by the solid points over these numbers here, 7, 8, 9, and so on, all the way to the right forever. Okay, so there's what's called set builder notation, a graph, a picture of these numbers, a picture of the solutions, the numbers that make my original inequality true. And then lastly is something called interval notation. All right, now look at my graph. All right, I'm going to be writing the interval notation representation of the solution set. Now look at this graph. Notice that there is a piece of the graph over here, then there's a big gap, big space and nothing, and then a second separate piece. So you're going to be writing an interval for each piece, right? So there's a piece here, so that deserves an interval, and a piece over here that deserves an interval. And then we'll have a nice little symbol for the word or. And again, if you've seen my videos on intersections and unions, you know what the symbol for or is, right? It's the union symbol. All right, so for this left piece, you go low to high. When you're writing interval notation, you always go low numbers to high numbers, left to right in this case. In this piece, the number at the left end, where is the left end of this piece? Well, there is no left end, right? That arrow indicates that it's going that way forever. So to indicate that this piece has no left end, we put a -infinity, right? Indicating a concept, the concept that this goes to the left forever. So this is not a number, right? I think I've mentioned this in videos before. Negative infinity, positive infinity, those are not numbers. Those are ideas. All right, then a comma. All right, and then we got all the numbers from the far left all the way up until, and then the right end of this piece is at -6. All right, and then you cap these off, the left end and the right end of your interval, with either a parenthesis if a number at the end is not a solution, or a rectangular bracket if a number at an end is a solution. I said a second ago, negative infinity is not a number. So always you cap those infinities and negative infinities with parentheses, to indicate, that's not a number. It's not a solution. Right? You can't plug in negative infinity. That doesn't mean anything. Negative 6, though, we said was a solution. Right? Negative 6 is making this original inequality a true statement. So to indicate that negative 6 is a solution, cap that off with a rectangular bracket. All right, make little 90-degree angles here. Just make sure you don't rush these. Right? If you rush them, sometimes they look too curvy and look more like parentheses than a bracket. And the parentheses and brackets have totally different meanings. All right, and then so this interval represents this piece of the picture. This interval represents this part of the inequality, x less than or equal to negative 6. Then we have the word or involved, right? Our solutions are these numbers or these numbers. The word or, you're taking the union of two sets. So you'll see this, to connect the pieces, you'll see this big U shape. And remember, again, from a previous video, this is the union symbol, which again usually represents our inclusive or, right? The word or here. So our set of solutions are all these numbers, or so these numbers can be solutions too. So let's look at this other piece, right? This other inequality, x is greater than or equal to 6, these numbers. The left end of that piece begins at 6. So 6 and then comma, and then go from 6 onward. And is there a right end? No, this is going to the right forever. So to indicate that there's no right end, put positive infinity or just the infinity symbol. It's like a sideways 8. All right, then we cap these off just like this interval here. 6 is a solution. 6 does make my initial inequality a true statement when I plug it in. So a rectangular bracket on that 6. And infinity is not a number. So infinity can't be a solution. You always cap off the infinities or negative infinities with a parenthesis. All right, parenthesis. All right, so there we go. All right, all three of these here are perfect representations of the solutions to this inequality that I started with. All right, and so you got a picture of them, you got a description of them in set builder notation, and then you have these two intervals for each piece of the picture, connected by the word or the union symbol. Great. All right, so I'm going to keep going with this. I've got several more examples, and I'm going to be following the same 3 steps. We're isolating the absolute value, rewriting as an equivalent compound inequality, then solving the compound inequality and verifying solutions, and of course writing our solution set in these 3 ways. All right, so my next example involving absolute value greater than or equal to is this one here. All right, so the solve and write the solution set in set builder notation, interval notation, and make a graph. I have the absolute value of just x. Again, we'll get more complicated in later examples. The absolute value of x is greater than 5 halves or 2.5. 2.5, whatever you want to write over there, that's equivalent to 5 halves. Okay, great. So the absolute value is already isolated, right? This absolute value of x is already alone. There's nothing multiplied by it. It's not divided by anything. There's nothing added or subtracted to it. It's all by itself. Wonderful. And now I can write, now that I've isolated the absolute value, we're going to write an equivalent statement, right? So this statement here is equivalent to saying that the absolute value of x is greater than 2.5 means that x has to be more than 2.5 units away from 0. All right, so what numbers are 5 halves units away from 0? Well, one of them is positive 5 halves, so we have to be to the right of that, right, to be farther from that than that from 0. And the other one's negative 5 halves. and we'd have to be to the left of that to be farther than that many units from 0. So saying that the absolute value of x is greater than 5 halves means that x has to be less than negative 5 halves, right? These are all the numbers, this is all the numbers left of negative 5 halves, right? More than 5 halves units away from 0. Or, right, always or here with the greater than or greater than or equal to. Or this number x inside the absolute value symbol could be a number greater than positive 5 halves, right? This is all the numbers this is representing all the numbers to the right of 5 halves on the number line, right? Numbers that are farther than 5 halves units from 0. All right, and this is already solved, right? This compound inequality, each of these is already solved for, and then we're just finding the union of these two sets. The variables are already alone on their own side, so I'm going to underline that's a perfect description of the solutions of this absolute value inequality. And you can try it out, practice with some examples, see if they work. Pick any number less than negative 2.5, like negative 3, negative 4, negative 5. Plug them in. Say negative 5. Plug in negative 5 for x, you take the absolute value of that, you get positive 5, and is positive 5 greater than 5 halves? Yeah, it is. 5 is greater than 2.5. That works. And it should work for any number you pick that's less than negative 5 halves. And, and then try the other ones. These numbers are also solutions. X is greater than positive 5 halves. So pick a number greater than 2.5, like 3, 4, 5, 6, 7. Plug in 7 for x. The absolute value of 7 is 7. 7 is indeed greater than 2.5. Those work too. All right, so then the ways we're going to describe or represent our solution set here. One is that set builder notation, right? All the solutions of this inequality are all the values of x such that, and then again I just write my solution to the compound inequality. All the values of x such that x is less than negative 5 halves or x is greater than positive 5 halves. Close that off. We could also draw a graph of this set of solutions. Right, here's the number line. You got 0 somewhere separating positives from negatives, and then we've got, I'll draw this the picture of this inequality first. X is less than negative 5 halves. Well, negative 5 halves would be to the left of 0. And it's all the numbers less than 5 halves, but not equal. Negative 5 halves is not a solution, right? The absolute value of negative 5 halves would be 5 halves, and 5 halves is not greater than 5 halves. It's equal to 5 halves. All right, so negative 5 halves is not a solution, so I'm going to indicate that by putting an open point or a hole or an empty point above it. Or you could also be putting a parenthesis. You might see other books where they put a parenthesis. And then all these numbers, I'm looking for the numbers less than negative 5 halves, right? To the left, negative 3, negative 4, negative 5, negative 6, and so on. Forever, right? A little arrow. Or, right, other solutions involved are these numbers here, right? All the values of x greater than positive 5 halves. So positive 5 halves, that'd be to the right of 0. And, greater than 5 halves, but not equal to 5 halves, right? So open point again above 5 halves. And all the numbers greater than 5 halves, 3, 4, 5, 6, 7, and so on are this way, right, to the right of 5 halves. And here is a nice little picture showing us where all the solutions of my inequality are, right, on the real number line. All right, and then now that I've got this graph up, it'll be easy to draw an interval or interval notation. Again, here I have two separate pieces, right? There's a big break in it here between negative 5 halves and 5 halves. So you write an interval for each piece, right? Basically an interval for each of these inequalities, and then the union symbol to represent that this is an OR statement, an OR inequality. So the left piece, again, you always go left to right, low to high when you write things in interval notation. There is no left end, so again, this negative infinity to represent that. The right end is at negative 5 halves. Negative infinity is not a solution, right, because it's not a number, so a parenthesis on that. Negative 5 halves is also not a solution, so a parenthesis on that. Or, right? The union with, the union symbol. And then I'll draw another interval for this second piece, which, the left end of that piece is at positive 5/2, comma. There is no right end to that second piece, so positive infinity. 5/2 is not a solution, parenthesis. Infinity is not a solution, it's not a number, parenthesis, right? And there's your interval notation for these, the picture of these solutions here. For all the numbers described by this set, or all the numbers described by this graph, are also described by these intervals, or by this interval here. Great. And that's it, right, for those first two. Now notice these first two examples, I had the absolute value of just plain old x, right? So once I changed to my equivalent compound inequality, it was already basically solved for. It was already done pretty much. That's not always going to be the case. So my next couple examples are on scenarios like that. So I've got the absolute value of x plus 3 is greater, right, than 4. This has the same form that all the examples I have in this video are going to try to look like, right? I want them to look like. Or I have the absolute value of some expression, some number x plus 3 is greater than, and over here hopefully I have some non-negative number so that the thing has meaning or more meaning. So it's already the way I want it, right? The absolute value is isolated. So now I can write this equivalent compound inequality. Right? All right, so here, if you go back to my first page in this video, remember how we were writing the equivalent compound inequality right here. Well, this time the a is this whole expression x plus 3, and then you have is greater than, and then the n is this non-negative number 4. So I have x plus 3 for the a's, and then 4 for the n, and negative 4 for the opposite of n. But again, you could also just think of what absolute value means. What is the definition? It's this distance from 0 on the number line. So what we're looking for here are, what numbers, what could x plus 3 possibly be so that their absolute value is greater than 4. Now, to have an absolute value greater than 4 means that you are more than 4 units away from 0. So this is equivalent to saying that the x plus 3, right, the number inside this absolute value symbol, that x plus 3 could be a number less than negative 4, right? Because if you're less than negative 4, you're left of negative 4 on the number line. That means you're farther than 4 units from 0. Right? Have an absolute value greater than 4, like it wants, like it says. Or, you could be a number less than, to the left of negative 4, or you could be a number, right? This x plus 3 could be a number greater than positive 4. Right? Being greater than positive 4 means to the right of positive 4, which is more than 4 units from 0. All those numbers have an absolute value greater than 4. All right, so now we have our equivalent compound inequality involving the word or. And then I solve this compound inequality. Now remember, to solve inequalities involving the word or, you solve each one separately, and then take the union of those solution sets. All right, so the left inequality, I'd be subtracting 3 from both sides, leaving me with x is less than negative 7. Or, and then the other inequality, same thing, I'd be subtracting 3 from both sides, and that leaves me with the inequality x is greater than positive 1. And now both inequalities are solved for, and there you go. And again, keep it with the word or. Do not connect these in any way. I'll write that off to the side here. Do not do this. Where you see x is less than negative 7, or x is greater than 1, and then people tend to want to put these together. They're like, oh, there's two inequalities, and I remember seeing something where they put the variable alone in the middle and said, oh, it's less than -7, or x is greater than 1, greater than 1, like that. X is greater than 1, x is less than -7. Don't put an or inequality together. Don't connect. Again, don't connect an or inequality. You can only do that with certain and inequalities, and not all of them. You can only do it with certain and inequalities when your solutions end up being between two values. You only connect inequalities when you're between two values. And why is this no good? Look at it. It doesn't make sense, because if the number on the left, you're saying here that 1 is less than -7. All right, this would be saying that 1 is less than -7 if you actually read it from left to right. That is wrong, right? That is an incorrect statement. Sorry, that's a G. So that's why you don't connect your or inequalities, because you end up making nonsensical statements. You end up making statements that are wrong, make no sense. Okay. So leave it with the word or between them. All right. Okay, so there's a perfect description now of all the solutions of this inequality, and we can check some numbers. Take a number less than -7, so like -8, -9, -10. How about -10? I plug in -10 for x. -10 plus 3 would be -7, and then we're taking the absolute value, which would be +7. Is 7 greater than 4? Yeah. And all the numbers less than -7 should do that, should make that a true statement. Try it out. Or, and all these numbers over here, try these out. How about numbers greater than 1? Like 2, 3, 4, how about 3? I plug in 3 for x. 3 plus 3 is 6. We're taking the absolute value of 6 is 6. Is 6 greater than 4? Yes, it is. So then again, try it with a bunch, just to see if you believe it. All the numbers greater than 1 should make this a true statement. All right, so I have a nice perfect description now of all the solutions. And let's express those in the three ways we've been asked to express them, right? Set builder notation. The solution set of this inequality here is the set of all values of x, as long as those values of x are less than -7 or greater than 1. And again, all I really do after is write my solution to the compound inequality after the description bar, right, after the bar. Then I'll make a graph on the number line, a little picture of the solutions. So here's a number line. Got 0 somewhere, and then just drawing a picture of each of these, right? Each of these belongs to the union, right? Remember the union of two sets. If you're in one set, you belong, or if you're in the other set, you belong, or if you're in both, you belong, right? It's the inclusive or very non-restrictive. All right, so all the numbers less than -7, right? Well, -7 will be to the left of 0, but not equal to -7, right? -7 would not work here. You'd have 4 is greater than 4. 4 is not greater than 4. It's equal to 4. So -7 doesn't work. Put a little open point, or again parentheses up there if you want. I like the open points. And then all the numbers less than 7, -8, -9, -10, and so on, forever, are solutions. Little arrow there. Or all the numbers greater than +1, right? +1 is to the right of 0 here. All the numbers greater than +1, but not equal to +1, right? So +1 is not a solution. And then all the numbers greater than 1, 2, 3, 4, 5, 6, and so on are this way. And there is a nice picture of our solution set, all the numbers that make our initial inequality a true statement. All right, and then just like it's very similar to the past three examples, several examples, couple examples. I've got a graph there where there are two separate pieces, right, with a gap between them. So I write an interval for each piece, and basically for each inequality, and connect it with the word or a symbol for the word or, that union symbol. All right, so the first piece, there's no left end, right? So -infinity comma, the right end of that first piece is at -7. Negative infinity is not a number, so parentheses, and -7 is not a solution, so also parentheses. And or, right, in union with, and then this other piece, the left end is at 1, comma, the right end, there is no right end, so infinity. 1 is not a solution, parenthesis. Infinity is not a solution because it's not a number, also parentheses again. All three of these things describe the same set of numbers, the numbers less than -7 or the numbers greater than 1, which are all solutions, all numbers that make this inequality that I started with a true statement. Wonderful. All right. So I've got another one like this where there's a more complicated linear expression inside the absolute value symbols, but nothing really changes all that much. You're going to see doing the same steps over and over again. And just keep paying attention to the direction of my inequalities. All right, so here I have the absolute value of 4x minus 3 is greater than or equal to 5. So again, it's already set up the way I want. The absolute value is on its own, it's isolated. So now, since that absolute value is isolated, I can now write an equivalent expression. And just remember what absolute value means. It's like the distance from 0 on the number line, right? What does it mean to have an absolute value greater than 5? Having an absolute value greater than 5 means that you're a number that is farther than 5 units from 0. So you're to the right of 5 or to the left of -5 on the number line. So this number here, this number inside the absolute value symbol, so that 4x minus 3 could be to the left of -5, meaning less than, and we could also, or equal to -5, less than or equal to -5. All right, this is all the numbers that are at -5 or left of -5 on the number line. And those numbers have an absolute value greater than 5 or equal to 5. Or if you're not to the left of -5, if you have an absolute value greater than 5, you could be to the right of +5. So this number, this 4x minus 3, this expression inside the absolute value symbols, could be greater than or equal to +5. These are representing all the numbers to the right of 5. Right, more than 5 units away from 0 has an absolute value greater than 5, or again, or equal to 5. All right, so here's my equivalent compound inequality involving the word or. Wonderful. No absolute value symbols anymore. Then I just solve each of these, and we'll verify that they're pretty good solutions, and just do a few little quick checks, and then write the solutions in set builder and in graph and interval notation. All right, so for this one on the left, I'd first, to solve for x, I'd first be adding 3 to both sides. That would leave me with 4x on the left is less than or equal to -2 on the right. And then I would divide both sides by +4, right? And dividing by a positive number does not change the inequality's direction. So you'd have x is still less than or equal to, and then -2 divided by +4 would be negative, and then 2/4 reduces to 1/2. All right, so x could be a number less than or equal to -1/2, or one of these numbers over here. Here I'd be adding 3 to both sides, and it gives me 4x is greater than or equal to 8. And then again dividing by +4, and the inequality direction will not change. X is greater than or equal to +2. All right, so here's a nice description of our solutions. And again, let's check some. Plug in -1/2, right? -1/2 should be a solution. You'd get 5 equals 5. All right. And that's true. 5 is greater than or equal to 5. That's true. Plug in any number less than -1/2, like -1, -2. How about -2? 4 times -2 is -8. -8 minus 3 would be -11. And then you take the absolute value, of negative 11 is positive 11. You'd have 11 on the left is greater than or equal to 5. Well, yeah, 11 is greater than 5. That works. So there's a description of some solutions. Again, try some more if you want, just so you believe it. But that's pretty good. Or these numbers over here. Plug in 2. Again, you'd get 5 is greater than or equal to 5. That's true because of the equal to part. But plug in a number greater than 2. 3, 4, 5, 6, 7. Plug in 7. 4 times 7 is 28. 28 minus 3 is 25. The absolute value of 25 is 25. You'd have 25 is greater than or equal to 5. That's true. Any number greater than 2 will make this thing work as well. So there's a nice little description after solving my compound inequality involving the word or, a nice description of all the solutions, all the numbers I can plug in and make this original inequality a true statement. Alright, and then the three ways we're going to represent that, right? The set builder. Alright, the solutions of this inequality is the set of all values of x as long as those values of x are less than or equal to negative 1/2 or greater than or equal to 2. The graph and number line here, pop a 0 somewhere, right, to separate positives from negatives, and just drawing a little picture of each of these inequalities. They'll both be part of the union. All the numbers here in either set will be part of the union. X is less than or equal to negative 1/2, right? So negative 1/2, that'd be to the left of 0 somewhere, right? And it's less than or equal to negative 1/2, right? So negative 1/2 is a solution. So I'm going to put a closed point above it or a rectangular bracket. And all the numbers less than negative 1/2 are these numbers to the left here, negative 1, negative 2, negative 3, and so on forever. Or all the numbers greater than or equal to positive 2, right? Positive 2 is to the right of 0 somewhere. Just put it there. And it's greater than or equal to 2. So 2 is a solution. Again, you can check that, plug it in to the original, and it'll make it true. And all the numbers greater than 2, 3, 4, 5, 6, 7, that way forever. And there's a nice little picture of our solution set. And then off to the side here, because I don't feel like throwing another page under this, the interval notation for this. Again, like the previous examples, I have a picture here where there are two separate pieces and a gap between them. The interval for this first piece should be, from negative infinity, because there's no left end, up until negative 1/2. Negative infinity is not a number, so it's not a solution, parentheses. Negative 1/2 is a solution, right? And because it is a solution, put one of those rectangular brackets around it, right? Make sure you don't rush this, right? Or, right? Or they, in union with, and the other numbers, the other piece. This left end is at 2, comma, there is no right end, so infinity, and 2 is a solution. So a rectangular bracket around that 2. Infinity is not a number, so it is not a solution, parentheses. Alright, so again, all three of these things describe the same set of numbers, right? These solutions to my inequality that I started with. Alright, any number less than or equal to negative 1/2 or any number greater than or equal to 2 will make this work, will make this true. Wonderful. Okay, alright, now I got another example here like this where something tricky happens in the middle of it. So far I haven't ever divided or multiplied by a negative number. And just recall that whenever you multiply or divide both sides of an inequality by a negative number, the inequality changes direction. The symbol flips around. So just keep that in mind when you're solving inequalities. Alright, so here I've got the absolute value already isolated, right? It's the same as the other ones. Absolute value alone, absolute value of negative 3x plus 2 is greater than, and then again a nice non-negative number over here, 7. So since it's already in that form I like, alright, the absolute value alone is greater than some number, I can change it to its equivalent compound inequality involving the word or. So remember what it means to have an absolute value greater than 7. That means you are a number. This negative 3x plus 2 is a number that's more than 7 units away from 0. So this negative 3x plus 2 is either to the left of negative 7, right? So less than negative 7, right? Those are numbers more than 7 units away from 0. Or the negative 3x plus 2, the number inside the absolute value symbol, is to the right of 7, is greater than positive 7, right? These are all the numbers greater than positive 7, or to the right of 7 on the number line, and those are more than 7 units away from 0, have an absolute value greater than 7. All right, so I've set up my equivalent compound inequality. We're going to solve each of these, right? So this would involve I'd be for this left inequality, I'd be subtracting 2 from both sides first. All right, it gives me negative 3x on the left is less than, and then negative 9 on the right. All right, then here comes the tricky part, right? To get x alone, I'd be dividing both sides by negative 3. All right, and that's where the trick comes in. It's not really a trick, it's just what happens when you multiply or divide both sides of an inequality by a negative number, and I've divided by a negative number here. So I'd have x on the left, right, the negative 3's divide out, and then the direction of the inequality changes. Instead of is less than, it becomes is greater than, and then negative 9 divided by negative 3 would be positive 3. Right? So I could replace x with a number greater than 3, or, and then same thing over here. I'm going to subtract 2 from both sides of this inequality to start. Then we'd have negative 3x is greater than 5. And then I divide both sides by a negative number. All right, dividing by negative 3 causes that change in direction of the inequality. So I have x on the left, and then instead of is greater than, now that becomes is less than, and then positive divided by negative is negative, and then 5/3 is as reduced as that gets. So negative 5/3, or negative 1 2/3 if you want to write a mixed number. But now let's see, I'll underline them now. Let's just check on some numbers here. See if this actually is a good description of some solutions to this inequality. So how about numbers greater than 3? Pick a number greater than 3. 4, 5, 6, 3.5, pi, remember that's like 3.14159 and so on. Pick a number greater than 3. I'll say 5. All right, I pick a number greater than 3. Negative 3 times 5 is negative 15. Negative 15 plus 2 would be negative 13. And then you're taking the absolute value. The absolute value of negative 13 would be positive 13. And is 13 greater than 7? Yes. So it seems to me like this is good, right? Numbers greater than 3 work. So those are solutions. Or, again, let's pick some numbers over here. X is less than this is negative 1 2/3, right? Negative 5/3. So what's a number less than negative 5/3? So negative 2, negative 3, negative 4. How about negative 3? All right. I'll take a number less than negative 5/3. Negative 3 for x. Well, negative 3 times negative 3 will be positive 9. 9 plus 2 is 11. The absolute value of 11 is 11. Is 11 greater than 7? Yeah, it looks like this also represents good solutions. All right. Okay. So now that I have a description of my solutions, they can be a number greater than 3 or less than negative 5/3. I'll write my solutions in those 3 representations that were given every single one of these problems here. Set builder notation. All right, the solutions of this inequality are any value of x as long as that value of x is greater than 3 or that value of x is less than negative 5/3. Right? Just again, writing the solutions to my compound inequality after the bar. A description of the solutions. A graph. And here's a little number line here. A little 0. And basically just drawing the numbers that satisfy each inequality in here, right? The numbers that would belong to the union of the solution sets. X is greater than 3. Well, it's positive 3, so to the right is 0 here. And it's all the numbers greater than 3, but not 3 itself, right? So a nice open point above 3. And all the numbers greater than 3, 4, 5, 6, 7, 8, and so on, are to the right forever. Or, all the numbers less than negative 5/3 seem to be working, right? And then negative 5/3 would be to the left of 0 here. And again, less than negative 5/3, but not equal, right? So an open point again above negative 5/3. And all the numbers less than that, negative 2, negative 3, negative 4, that to the left forever. And then off to the side again, we'll put our interval notation. Same as always, not always, but same as all the examples here so far. Two pieces, right? Two separate pieces with a gap, a hole between them. So two separate intervals. The left one, from negative infinity up until negative 5/3, right? Always parentheses on the infinities and parentheses on the negative 5/3 because it's not a solution. Or, right, in union with. Then the other piece, left end is at 3, comma, right end, there is no right end, so infinity. 3 is not a solution, we've said, right? So open parenthesis there. And infinity is not a solution because, it is not a number. Okay. Now, that's it there for that one. Right? All three of these, again, represent the same set of numbers, the set of solutions, all the numbers that make this a true statement, the original inequality. Okay. So my next example might be a little tricky. So far, we've had the absolute value alone on one side, and then a positive number on the other. Right? It was positive 7 here. For my first example, it was positive 6, and then, positive 4 in another one. But I always had, in these examples so far, I've had the absolute value alone, is greater than or equal to, and then some positive number. Well, what if this number isn't positive? What if this number is, 0 or negative even? And that's what my last three examples deal with. All right, so let's take a look at these. So my next example, you have the absolute value of 2x plus 5, and then after that, minus 2, and that's all on the left side, is greater than minus 2 or negative 2. All right, so here's one where the absolute value is not isolated. Okay, so I must, the first step I want to follow is I want to isolate the absolute value, this absolute value of 2x plus 5, get that alone on its own side. So that means I want to remove this term of negative 2, and to do that I would have to add 2 and do it to both sides. Alright, so the left side becomes the absolute value of 2x plus 5 is greater than, and then 0. It's greater than 0. Alright, now think of what numbers have an absolute value greater than 0. Basically every number except 0. Alright, I'll write that off to the side here. Right? Every number except 0 has an absolute value greater than 0. Oops, sorry, has an absolute value greater than 0. And 0 is still not negative, right? When I went back, if I go back to my first page again, if I go back to that first page, when I'm looking at things of this form, I probably should have written this earlier, but I would like this number over here to be non-negative. Alright. Or if it's negative, we'll talk about that in a little bit. Now 0, right? 0 is non-negative. So having an absolute value, greater than 0 actually has meaning. So we can still do this. We can still do our second step. Rewrite the absolute value inequality as an equivalent. All right, so I'm going to do that where, the a is the 2x plus 5, and the n, this non-negative number, is 0, right? 0 is non-negative, and we'll go from here. All right, so what's the equivalent compound inequality involving the word or? Right. So this absolute value of 2x plus 5 greater than 0 is equivalent to, well, again, this thing, what numbers have an absolute value greater than 0? Well, every number but 0, said that here. So every number to the left of 0, so this 2x plus 5 could be less than 0, left of 0. Those numbers have an absolute value greater than 0. They're more than 0 units away from 0. Or any number to the right of 0 as well on the number line has an absolute value greater than 0. So the 2x plus 5 could also be a number greater than 0. Right, so there's I've isolated the absolute value, and then as in the other examples, I rewrote this as an equivalent compound inequality involving the word or. All right, and then we're solving these. I would subtract 5 from both sides, leaving me with 2x is less than negative 5. Then dividing both sides by positive 2, getting x is less than negative 5 halves, or, and then doing the same to this one, solving this one, subtracting 5 from both sides gives me 2x is greater than negative 5, dividing both sides by positive 2, x is greater than negative 5 halves. And again, I'll underline these here. These look good. Let's check them out. So all the numbers less than negative 2.5, are they solutions? So let's take a number less than negative 2.5, see if we believe it. A number less than negative 2.5 would be like negative 3 or negative 4 or negative 5. Let me take negative 3. Put it in here. 2 times negative 3 is negative 6. Negative 6 plus 5 is negative 1. The absolute value of negative 1 is positive 1. Then 1 minus 2 is negative 1. Is negative 1 on the left greater than negative 2? Yes, it is. Negative 1 is greater than negative 2, right? Negative 1 is to the right of negative 2 on the number line, so it's considered greater. So I'm believing this, that the numbers less than negative 5 halves are solutions. Do I believe this as well? Let's see. How about numbers greater than negative 2.5, like negative 2 or negative 1 or 0? Or how about just 0? I'll just pick 0. Plug in 0 for x. 2 times 0 is 0, plus 5 is 5. The absolute value of 5 is 5. 5 minus 2 is 3. Is 3 on the left greater than negative 2? Well, yes. Any positive number is greater than any negative number. 3 is definitely greater than negative 2, so I am believing this as well. This seems to be a good description of all my solutions. All right, so the way I'm going to write the set builder notation, let me show you a couple ways we could do this. Notice that our solutions here are all the numbers to the left of negative 5 halves or all the numbers to the right of negative 5 halves. What's the only one missing? Negative 5 halves, right? Negative 5 halves itself. Negative 2.5 is the only number here on the real number line that is not a solution. So I can do this set builder thing a couple ways. Let me show you. I could do it the way I've been normally doing it, right? The set of all the solutions to this original inequality, right? The set of all solutions to that inequality are all the values of x, as long as the value of x is less than negative 5 halves or the value of x is greater than negative 5 halves. And that's all well and good. This is perfectly fine to write it this way. But you could also write this, say, the set of all the solutions to this inequality that I started with, right? Again, this one back up here. The set of all the solutions are, all the values of x, as long as x is not equal to negative 5 halves, right? Because like I said a second ago, you can plug in any real number, right? Anything to the left of negative 5 halves. Anything to the right of negative 5 halves, you can plug in any real number except negative 5 halves. So this is a very short way of writing this same statement, that x cannot be negative 5 halves. It doesn't matter though, either way is fine. Alright, then we'll make a graph of the solutions. So here's a number line, right? The number 0, and again, just drawing a picture of both of these. So x is less than, but not equal to negative 5 halves, right? So that's over here to the left of 0. There's negative 2.5, and x is less than, but not equal. So a nice hole there. Again, this is, I know I drew something, but technically there's nothing there, right? There's a gap, a hole, empty space, telling me that negative 5 halves is not a solution. And all the numbers less than negative 5 halves are these numbers, right? Negative 3, negative 4, negative 5, etc. To the left forever. Or all the numbers greater than negative 5 halves. So all the numbers, to the right of negative 5 halves. Again, everything except the hole at negative 5 halves. Great. And then the interval notation. Now I know it doesn't look like it, but this is exactly like all the other examples so far. This is technically two pieces, right? Because remember, this is a gap. This is a hole in the graph. All right. So it's really, I know I have drawing. I know I drew something, but technically that's not supposed to be there. There's nothing there. It's empty space. So I do have two separate pieces on this graph, just like in all the other graphs. It's just that the gap between them isn't as large. Right, the gap between them is just one number large. Right, but because I still have these two separate pieces, right, when I write the interval notation, I'm still going to write the two intervals. So this piece on the left, right, there's no left end, so negative infinity, comma. The right end of that left piece is ending at negative 5 halves, right? And negative infinity is not a number, so parentheses. Negative 5 halves is not a solution, right? Parentheses again. And then we have or, right? Or, put the in union with. And then the right part of the graph, right? This right piece after the gap, after the hole. Its left end is starting at negative 5 halves, and there is no right end, so it's going to infinity. And negative 5 halves is not a solution, so parentheses, and infinity is not a solution because it's not a number, also parentheses. So here's the interval notation for all these numbers, every number on the real number line except negative 5 halves. All right, you got two pieces, a gap at negative 5 halves. Great, so all three of these things, well really all four of them because I had two set builder notations, all four of these things represent the same set of numbers, all the numbers that make my original inequality a true statement. Great. All right, just got a couple more. Oh, it's pretty long, all right, but bear with me here. So there's another one where the other side has the number 0. Now it's nice because the absolute value is already isolated. I don't have to do anything. It's already absolute value alone is greater than or equal to, and then again 0 on the other side. All right. Now this one is a little different than the last one. Right? The last one you had the absolute value being just greater than 0. All right. Here, I have the absolute value isolated, and I say what numbers have an absolute value greater than 0 or equal to 0? That's every number. Every real number. Has an absolute value greater than or equal to 0. That's not two. That should be two words, or equal. Sorry. Every number, right? 0 has an absolute value of 0, which is equal to 0, right? The equal to part. And all the numbers to the right of 0 have an absolute value greater than 0. All the numbers to the left of 0 have an absolute value greater than 0. So if you recognize that, you say I have an absolute value of some number, when is that greater than or equal to 0? This is always true, right? So this inequality is always true. So that means every real number is a solution. Okay, so one way to indicate that, if you want to do set builder, is, all the solutions to this inequality are all the values of x that is just any real number, such that x is real. All right, just do a x is any real number. You plug in anything you want, and this will be true. Plug in 1,000,000, plug in 2/3, plug in -7, plug in 0, plug in 5/6, plug in 6/5, plug in 7/8, 1,000,000, billion, trillion, whatever you want, and this will be a true statement. And so the graph, right, here's the number line, 0 and so on. The graph, I'm just simply going to draw a little solid point over everything, right? Every single number works in this inequality. All right, and then for the interval, now this is a little different than all the examples we've seen, right? Every example in this video up till now has had two separate pieces, some sort of hole or gap between them. This is not two pieces. This is one solid piece. So I'm only going to need to write one interval. And is there a left end? No, there is not. So I indicate that with -infinity, comma, and I go from my -infinity all the way up till, is there a right end? No, there is not. So I put in positive infinity. And cap these off. These are not numbers, so they don't belong to the set. They aren't solutions, so parentheses on those. This is the interval representation of all real numbers. That's another way of saying all real numbers are solutions. This -infinity to infinity interval. Okay. So again, I hope you recognize that. Now, if you don't recognize that, what would happen? All right. So say we didn't recognize this, and I decided, I'm going to continue following along with my little model here, right? Where I have the absolute value of something is greater than or equal to a non-negative number, right? That is exactly what's happening right here. I have the absolute value of something is greater than or equal to a non-negative number. So I can write it in this equivalent form here, this equivalent compound inequality with the word or. So what numbers have an absolute value greater than or equal to 0? Well, any number less than or equal to 0 would, so 6x minus 5 could be less than or equal to 0, or any number greater than or equal to 0 would as well. 6x minus 5 could also be greater than or equal to 0, and all I'm doing is again translating to this equivalent compound inequality with the word or from my first page in this video. And then in solving each of these, now I'm just going to say this, right? You would add 5 divided by 6, you would add 5 divided by 6. We'd have x is less than or equal to 5/6, or x is greater than or equal to 5/6. But isn't that just everything? If we try, here's a graph of this, right? Here's a number line, number 0 there, and then let me draw these. X is less than or equal to 5/6, so that's positive 5/6. That's over here. It's less than or equal to, so 5/6 is included, nice solid point above it, and all the numbers less than 5/6 are to the left, right? 0, -1, -1, and so on. All right, that's this piece, that's this part. Or all these numbers are solutions as well, and again, you can try some out, plug them in. Like I said, you can plug in whatever the hell you want, and it's still going to be true, right? And everything has an absolute value greater than or equal to 0. But now let's draw this other part. Greater than or equal to 5/6. So again, 5/6 is included, and all the numbers greater than 5/6 are to the right. And do you see how this graph I just made here is exactly this graph here, just without numbers labeled? It's one solid continuous piece from the far left forever to the far right forever, just like here. Every real number, right? It's the same as that graph there. It's every real number. Every real number is a solution to this inequality. All right. Wonderful. All right, so my final example, sorry about the length, I know it's a little over an hour here, but my final example, every single one we've seen so far has ended up with, absolute value of something on the left is greater than or equal to, and then a non-negative number. Well, my last example has a negative number on the other side. Ooh, right, scary. All right, so let's see what happens. This is, I have the absolute value alone, right? Absolute value of 2x plus 1 by itself already is greater than, and then, a negative number, right? So this time I have a negative number over here, negative 3. Well, you should know by now that when you take the absolute value of a number, the result will be non-negative, right? The absolute value of a number is a non-negative number. So what I have here is the left side is a non-negative number, the right side is a negative number, and we have is greater than. A non-negative number will always be greater than a negative number. Okay, so this inequality again will always be true. Just like the last example. Right, because a non-negative number will always be greater than a negative number. So just like the last one, I'm going to put it in set builder first. The solutions to this inequality are all the values of x as long as x is any real number, right? As long as x is real. The graph, same thing. It's just, anything. Right, here's the number line, there's 0. It's everything from the far left to the far right. Every number makes this a true statement. This will always be true. The interval, same as last time, right? From negative infinity up to infinity, from the far left to the far right, in parentheses on those. Right? All real numbers are solutions. A non-negative is always greater than a negative. Okay, now, what if, again, what if you didn't recognize this and say, I can just jump to the end here. I'm hoping you do. I'm hoping you'd see this and recognize that this has all real numbers as solutions. But what if you didn't, and I blindly followed that little translation from the first page, right, where you see I have absolute value of a greater than or equal to n is equivalent to a less than or equal to the opposite of n, or a greater than or equal to n. All right, so in my inequality up here, the 2x plus 1 is the a, right? That's the thing inside, the expression inside the absolute value symbols. And then is greater than, and then the number on the other side is n. And say you forgot that this had to be a non-negative number for some reason. All right, so I replace all the a's with 2x plus 1, all the n's with negative 3, and we get the following. The first part of the inequality, I'd have, 2x plus 1, the a, is less than, the opposite of n, negative n. Well, if n is negative 3, then the opposite of n would be positive 3. Okay? Or, and then the other one would be 2x plus 1, the a again, the 2x plus 1 here, is greater than, and then the n in this case, the number is negative 3. All right? And let's see what happens when I solve this compound inequality involving the word or, and we take a look at a graph. Right? So if I solve these, now I'm just going to jump to the end. Right? What would I be doing for this? I'd be subtracting 1, then dividing by 2. So this one here, I'd have x is less than 1 when I solve it, or, right, you subtract 1, that becomes 2, then divide by 2, that becomes 1. Here, I'd subtract 1, that'd make this negative 4, and then divide by 2, I'd have x is greater, and then, greater than negative 2. Right, you'd have a negative 4 divided by 2. And let's see what this looks like. Remember, you're doing OR here, so it's the union of these two sets, right? Let me show you a graph. Let me draw those. So here's the number line. You got 0. X is less than 1. That's this picture here. X is greater than negative 2. That's this picture here, but I'll draw it below. Now, if you take the union of these two sets. Remember, the union is, every number in one set belongs, or every number in the other set belongs, or any number in both also belongs. So all of these numbers belong to the left of 1. They belong to the union because they're in the first set. And all of these numbers belong to the left of -2 belong. Or, sorry, to the right of -2. All those numbers belong because they're in the set forever that way. Can you see how everything belongs? -2 is in this set, so it's in the union. 1 is in this set, so it's in the union. Everything, all real numbers, belong to this union. So even if you decided to do the way we've been doing all the other examples, and didn't see it right away that all real numbers were solutions, you would still come to the conclusion that all real numbers were solutions. Everything has to be a solution to this. Great. So just be careful, pay attention, especially to directions of the inequalities, right? Make sure the directions of your inequality symbols are proper, and pay attention to when numbers are non-negative or negative, and whether you have is great, again, is greater than or is less than symbols, or greater than or equal to, less than or equal to. And a lot to keep track of, I know, but you'll get the hang of it hopefully with plenty of practice. All right, and as I like to say at the end of these, do the best you can, try the best you can to learn the material on your own before you go looking for help. I have found that people who take the time and the effort to learn the material, understand the material on their own before they go asking for help, I find those people tend to remember the material better and for a longer period of time after they learned it. So read the material, of course. Read through the author's examples, perhaps even try to work on examples yourself before you see how the author did them, and then compare your work to the author's and see if you can learn from some mistakes there. Of course, work on plenty of exercises, practice problems, check answers when they're made available, if they're made available, just to check yourself, see how you're doing. And of course, don't give up after the first attempt at a problem. Very often there are several approaches that'll work for a math problem. So if after several approaches, several attempts at a problem, things still aren't working out, perhaps you should try reading through the material again. Maybe even a third time, more slowly, more deliberately. Take notes. Because if you've done some problems, chances are you have a better idea as to what the author is expecting of you. So then a second or third read through, will shed some more light on the subject, and you'll know better what you're looking for. You'll probably see some things that you didn't see the first time, or things will click the second or third time through that didn't click the first time, and it'll make it that much easier. Of course, if after that, if after several read-throughs of the material and several attempts at problems, if you're still not getting it, still not clicking, it's not a sign of weakness whatsoever to go out asking for help, go out looking for help. That is what other people are there for. So ask a teacher, a tutor, a friend, someone in the class who you know that knows the material well and is willing to help. Look for supplemental materials online. There's loads of it out there. Look for videos on the subject. There's lots of math videos out there, tons of them. Videos like this one, or other ones out there that are plenty shorter and better than this one. I assure you, you can find them. But just keep looking, keep persistent, stay persistent, keep practicing, don't give up. And I think the hardest part too is to try to keep a positive attitude. Right? It's amazing the difference a change in mindset can make. If you think you hate something, you think it's going to be boring, well, it's probably going to continue to be that way as long as you think it. Try to go into these sessions, your homework sessions, your readings, with an open mind, thinking I'm going to learn something today, I'm going to enjoy learning it, I'm going to enjoy reading this, I'm going to take something away from this for my life, for my school, for my whatever, and be positive about it. It's easier said than done, I know, but it's amazing the difference that kind of a change in attitude can make. So stay persistent, stay positive, keep practicing, don't give up, and I just know you can get it. I believe in you. All right, and thank you very much for watching.